Okay, so today we're talking about means, and we're going to do tests for means. So let's see what happens here. So this is our first lesson of, I believe, two in this, two or three, I forget. Actually, it might be three. Wow. Okay, so carrying out a specific test. So the conditions are the same as they were for intervals for means. So we need random sample, let's experiment, random sampling. Less than 10%, and then if the population is normal, this is the large sample condition, you're good. If n is greater than 30, you're good. Or if you graph it and it's not majorly skewed, no outliers, you're good. And again, sketch out the graph. If your third option there for large sample, you need to do a little sketch of the graph on your paper. Okay, so here are the lifetime in hours of 15 AAA batteries. That's the data there. Check if the conditions performing a specific test are met. Okay, so we're just going to check the conditions. So random sample, check. I would underline the word random sample, draw a little line to what you say random sample with a check mark. Less than 10%, so this is, 1, 2, 3, 4, 5, 6, 7, about 15, I guess 15 samples from all the batteries that were made that day, which is way more than 15. So we're good there on the less than 10% condition. And the last condition, so it might be a good idea, and you probably want to do this anyway, right? So I'm just going to put batteries, so battery, type in the data into a listen spreadsheet page. And 31. Okay, so you can graph that if you want to on a data statistics page, use battery. And so even if you did it by hand, your graph should look something like that. And it doesn't look majorly skewed and no real outliers that I see. So it passes the test. You're past a large sample condition. So this is what they did. Similar graph there. You can see sometimes the calculator, because of the way it kind of grouping things, it'll kind of highlight, it looks like they're stacked, but they're not really stacked. If you spread it out a little bit, you can see that. Okay. So this is the basic or generic kind of z-score here. So standardized test is the the value minus the parameter, in most cases the mean here, divided by the standard deviation. Ideally, this would be the formula, but we don't use Z because the population standard deviation is almost always unknown, and that's true. We just don't know it. So we tend to use S, the sample standard deviation, instead of the population standard deviation. And we use a T curve instead of a Z curve. So this is our formula for the test statistic here. The standardized test statistic is T, is X bar minus the null over a fraction, standard deviation, sample standard deviation divided by square root of n. Okay, which is like the standard error. That's divided by the standard error, essentially. Okay, degrees of freedoms, n minus 1. We've seen that before. There's only like 1 or 2 that was not that. This is stuff you've seen before with the T curve. As it gets higher and higher degree for n, or degrees of freedom, it becomes more and more normal. So it becomes not as wide and a little taller there. They're similar in shape. Teasers should have more variability, so they're wider at the base. More area, they have wider, fatter tails, so to speak, there. And again, like we just said, they tend to look more normal as n increases. You could use a table, but you're not going to use your calculator. So the null in that example was 30 hours. But we think maybe the new batteries are going to be more than 30 hours. So the alternate is we think that the average is going to be more than 30. So then you would plug in the data there for that problem. I think the X bar, well, let's just do it here. So if you go to going to go back to, I guess, the first page. So control left arrow goes back to the first page, which was the calculator page. Hit menu. So do this one, you go 6. This is a test, so I'm going to say 7. And this is not a 2-sample t-test. It's just a 1-sample t-test, which the calculator just calls t-test. So it's a 1-sample t-test for means. T is when it's means, Z is when it's proportions. And this is using data. So I'm going to choose battery there. Ooh. Oh, the null is, so the null is 30, right? The list is battery. And the frequency is that, and the alternate is, we think, greater than there. Okay, so we're going to do the test in our calculator. And so you can see that X bar is 33.93. That's where you can get that data from. Standard deviation, SX is 0.815. You can see 9.815, sorry, 9.82 is what they said. N is 15, so square root of 15 there in the formula. And the null is 30. And so you can plug all that in, and you see you get the correct t-value there of 1.55. So it does provide the t-value for you. Again, if you don't want to show that work, you're going to be okay with that. So if you just said t equals 1.55, if you basically list everything that's in the calculator there. So all of those values, if you just list them on your paper, that counts full credit for this, as long as you list the values correctly. If you have something wrong, you won't get any partial credit for that. So that's where we get those values from. Degrees of freedom, again, is n minus 1, so 15 minus 1 is 14. Good idea to check, just because every once in a while, one of these test reports have a different degrees of freedom method, and so just kind of checking your calculator by doing the test first. You go, oh, yeah, it's n minus 1 for this one, so I got it, because it does get, I think, mildly confusing at times. That's from the table, which we don't use. Okay. Okay, suppose you want to perform a test at the null is 5 versus the null is not equal to 5 for the mean there. At the 1% significance level, a random sample of size n equals 37 from a population of interest yields x bar equals 4.81, standard deviation is 0.365. Assume the conditions are met. Explain why the sample result gives some evidence for the alternate. Okay, so we think the alternate is, the alternate is it's not equal to 5. And we got a mean of 4.81. So that is at least different than 5. So we have some evidence, right? So it doesn't matter which direction it is as long as it's not 5 there. Can we calculate that? So this one we're going to use stats. So you go menu 6, 7 as a test. And again, it's a 1-sample t-test, so just a t-test in the calculator. And this time we're going to use stats. So the null was 5. X bar, it says it's 4.81. Standard deviation is 0.365. N is 37. And it defaults to the alternate being not equal to, which is correct in this case. And so you can do the test in your calculator. You can also show the work for that. So showing the work means plugging into that formula. You still get the same t-value of negative 3.17 degrees of freedom. Always list those values on your paper. So if you put them in the formula like that, that counts as listing those values. So that counts as listing X bar, listing the standard deviation, etc. But if you don't show the work, you definitely want to list all those values that are outputted in your calculator there, which is a really good thing to do. And they draw the normal curve, kind of sketch it out, see which way to go. So this is actually, I don't know if you noticed that the picture there, it's a two-sided, right, interval, because not equal to, there's actually a little tiny area in the left and a little tiny area in the right there. So it is a two-sided interval. So if you do norm CDF on this guy, it does take, you have to multiply it by 2. So that's what they're doing here. They're taking that value and multiplying by 2 when they do norm CDF to get that area. Okay, so, and again, you see that times 2 over there on the right? That's where that's coming from. To get the p-value, you have to do, one side or the other. They chose the left side, so negative infinity to negative 3.17 with the degrees of freedom of 36. and then they multiply that value by 2. If you see that in the thing multiplied by 2, that gives them the 0.0031 p-value. So it's really easy to forget that it's a two-sided one here. So don't forget, if you do it with TCDF here to find the p-value, that you multiply it by 2 because it's a two-sided one. These are the basic steps. So I have a plan for you. If you come to class, I have a worksheet for this, just to remind you with the example that we're about to do here in a minute. The conditions, again, if you want to think about the conditions, I think this is good to think about what they're connected to. Again, this is almost review, but it's good review. It's hard to remember this sometimes. So one, what condition is attached to the difference between X bar minus the null? That's the random condition. So we can't even really begin doing things if we don't have a random sample or if it's experiment random sampling. So that's important. To get the t-curve, that's you're proving kind of normality. In this case, for a t-curve, you're preparing for t-curve, so you have to do the large sample condition to choose that. So that's, is the data not majorly skewed, or the n values, greater than or equal to 30. And every time, I think in all these, before we do standard deviation, we have done the less than 10% condition. The only time that doesn't apply is for experiment or something like that, or occasionally. There might be one other case, but that's the main case. So it doesn't apply. So less than 10% condition seems to apply to most of these. And that's because we're sampling without replacement there. It's kind of proving independence of sorts. Suppose the conditions are met. To perform a test of the null, you would compute that. To find the p-value, calculate the probability, you have to think about the direction of this. So when it's greater than, you're shading to the right, less than, shading to the left, and not equal to, you're shading both directions there. Okay, so this one, the level of dissolved oxygen in a stream at a river is an important indicator of the water's ability to support aquatic life. A researcher measures the dissolved oxygen level at 15 randomly chosen locations around the spring. Here are the results in milligrams. So there they are. So you would then type this data into your calculator, because we're going to need to do this. So this is DO. And so this is going to be 4.53, 4. Okay, so I type in all the data. There's 15 pieces. That's good. Sometimes I skip one. So an average dissolved oxygen below 5 milligrams puts aquatic life at risk. Okay, so do the data provide convincing evidence for the alpha at 0.05 significance level? Okay, so we've got to go through the whole enchilada here, right? So we've got to, graph this data, check the conditions. So the conditions, does it say something about a random sample, randomly chosen location, so random sample? Is it less than 10%? So 15 randomly chosen locations. There's probably almost an infinite number of locations along the stream. So that's less than 10% of the location across the stream. Certainly does not look majorly skewed. I don't see any obvious outliers. So it passes all the conditions. So at this point, you want to start then go with the null, right? So the null is, I guess you probably could have started with the null, to be honest, it's the state. I guess I did that out of order. But the null is that we, nothing's unusual. 5 is what it is. But if it's less than 5, right? Because that last line in there says an average dissolved oxygen level below 5 puts aquatic life at risk. And the question was, is this stream at risk? So the question is the alternate, is it less than 5, right? So that should kind of flow from that. And the null is nothing's unusual. It's 5, right? This is not a big deal here. So we've got the alternate null. We define the variable mu is the true mean dissolved oxygen level in the stream using an alpha level of 0.05, because it said use alpha level of 0.05. So then you want to state the conditions. Again, we just stated the conditions a minute ago. They did a histogram kind of thing, and that's fine if you want to do that, but dot plots are the easiest to do, and so you can do that. On your Inspire, if you wanted to do that, let's see what happens. So plot type, histogram. Comes out a little weird. You could change the bin so it looks kind of like theirs if you wanted to, but again, it's just kind of showing off. You don't have to do all that. So then you want to type, again, if you show your work, you're plugging all those numbers into the formula. If you're doing this in the calculator, so you're going to add a calculator page, menu, 6, 7 is tests, and then t-test, it's a one sample t-test, and this time we are using data. The null is 5, the list is do, and so we should get the same values doing it this way. We do, t is negative 0.94, p-values 0.36. X bar, again, list all those values if you get your if you use your calculator to get the data from. I want you to know how to do this because again, there could be some questions in multiple choice where they don't show the negative 0.94, they show that the work there, and that's the answer basically. So I want you to know how to do that. So it's good practice. I think when you're learning it, I would do it by hand and check it in the calculator. On the real thing, I might just do it in the calculator or just double check your work if you need to make sure it's right. Again, so this is a one-sided test, so we don't have to double that. So you just do negative infinity, the upper is 20.94, and then 14 and that. So, okay. And because the p-value of that is less than the alpha level, 0.05, we fail to reject the null. So because 18% is bigger than 5%, we're going to fail to reject. We don't have evidence. We don't reject. We don't have evidence that the true mean DO level in the stream is less than 5. And that kind of makes sense. I mean, almost half of the values are more than 5. About half the values are less than 5. So I didn't expect it to be probably a convincing evidence here that was the case. Given conclusion in part A, what kind of mistake? So we failed to reject. This is a silly way to remember, but failed to reject is type 2. The word to, I know failed to reject doesn't mean the word to, but if you think of failed to reject as type 2, failed to reject, it could be a type 2 error there. So if we did, the true mean DO level in the stream is less than 5. We didn't find convincing evidence. That would imply aquatic life in the stream is at risk, but we weren't able to detect that fact, so that could be harmful to the environment there. If you just give a calculator results with no work and one or more values are wrong, you probably won't get any credit for that. Name the procedure, so that's important. So the one sample t-test for means, and report the standardized test statistic, the degrees of freedom, and the p-value. So those are the important ones. I write all those down from the calculator just to be sure, but those are the three and the name of the test. So it's important to remember the name of the test. I wasn't emphasizing that, but if you use the calculator method, that would be the way to go there.